Example 3. Compare the values of delta y and dy when y is fx, that is this cube function, okay, and x changes from 2 to 2.05 and another option 2 to 2.01. Now let's look at delta y versus dy. So f at 2 and f at 2.05 have been calculated. Okay. So delta y is the difference between the actual values. Dy is derivative of f at x times dx. So find the derivative and now evaluate at 2. 2 is your original x, and delta x. Delta x is the difference between x, x1 and x2. So you got two values, right? So we are using x1 and x2. So that's your delta x. Oops, where did we go? There. 0.05. So you are placing 0.05 there because dx is same as delta x. And dy, when you calculate, you get this. Look, dy is close to delta y. Delta y is the actual difference between values. Dy gives you an approximation because it's going to use f prime. In other words, it's using the linearization. Likewise, for the second case, f at 2.01 is this. So delta y is the decimal part of it, whereas dx is the same, 0.01. When you use it, look, this is close to this. All right. Final example illustrates the use of differentials in estimating the errors. All right. Now, suppose you have radius of a sphere. It's measured is 21 centimeters with a possible error to be at most 0.05 centimeters. So that is delta r. What is the maximum error? So volume is this. If the error in the measured value of r is delta r, which is dr, then the corresponding error in the value of v is delta v. Delta v can be approximated by dv. So dv requires derivative of this. So 3 comes down, cancels. So 4 pi r squared and then dr. So the dr is 0.05, r is 21, and you can approximately find dv. So the maximum error in the calculated volume is about 277 centimeters cubed. Notice the possible error. Possible error, actual error is delta v. Delta v, so possible error may appear to be rather large. Okay, so 277 looks very large. Well, so you need to understand in comparison to what, right? 277 may be very large in comparison to, I don't know, 500. That's a big error to talk about. But if it is in comparison to 5 million or something, then it's a small error. So that's why you need to understand relative error. Relative error is this quotient, delta v over v. Delta v is approximated by dv, so dv over v. So once you simplify all this, you get this, and now evaluate it. So that's a very small amount. So it's a basically 0.24 percentage in radius and 0.7 percentage in the volume. So it's a very small error you're looking at. Okay, so this completes the theory part of section 2.9. Next videos will cover problems from web work. Until then.